Hello, let's look at reactions of aldehyde. The carbonyl group has delta minus on the oxygen and delta plus on the carbon due to the electronegativity of oxygen. Now we can look at a reagent where you have a E, that's the electrophilic portion of it, and a nucleophilic portion of the reagent. So a good example is something like HCl. So H is delta plus, Cl is delta minus. Now what's the fastest reaction can take place is protonation of the oxygen. So the lone pairs on the oxygen will attack and abstract a proton doing a protonation. So that's very fast reaction, takes place quickly. Now what happens? The Cl is released as nucleophile, or it's a leaving group you can think, but it's actually a nucleophile. So I'm just showing only pair of electrons, but there's octet there. But this nucleophile attacks on the electrophilic carbon or delta plus carbon. As a result, the pi bond opens up to the oxygen because it's already protonated and it has too many bonds by now. So the numerical 1, 2, 3, 4 is kind of the order to think. Now what happened now? So we got the pi bond broken and the oxygen and the hydrogens intact, but O negative easily going to find out a proton. Well, actually there is the proton already, so it's going to sit there. So it's a single bond, bonds are fine. And then the chlorine is attached with a new bond. So that's the nucleophile. So it's a nucleophilic addition, right? So triggered by the protonation, but it's a nucleophilic addition. So now we can think overall what happened is the sp2 carbonyl broke the pi bond. The sp2 carbonyl is actually trigonal planar, so it can be attacked from the top or the bottom. So eventually you got the sp3 compound, right? So let's look at few examples without going into the mechanisms, but I explained just to see like why these reactions takes place, right? The mechanism is separated, but I put few examples of aldehydes. Look at this one, typical alkyl aldehydes, and then CH3COH, acetaldehyde, and then the benzaldehyde. So any of these ones show common reactions. So the first one I want to look at is oxidation. So where are the oxygens available? Permanganate, dichromate, chromate, things like that. So these ones are mostly under acidic conditions, will be reacting and adding oxygens, right? So that's the major reaction. So aldehyde will be oxidized into the maximum level, which is carboxylic acid. So under acidic conditions, you can recover carboxylic acid, the relevant one. If it is benzaldehyde, you will end up with benzoic acid, right? Now the opposite also can work. What's that? Reductions. So basically adding hydrogens. Where we have hydrogens, lithium aluminum hydride, 4 hydrogens there, and also sodium borohydride, there's 4 hydrogens. So this is a reduction. There are other reductions too. Industrial type of reductions, nickel and hydrogen can be added. That's a different thing. But the reagents are lithium aluminum hydride and sodium borohydride. So first one is stronger, second one is much milder. But what happens, instead of the double bond O, you're going to get 2 hydrogens, right? Again, I'm neglecting the mechanism though. So the mechanism has to be discussed separately. So on the oxidation, you put a double bond O. In the reduction, you put 2 hydrogens on the same place, right? So that's a simple way to look at it. Now, also, just remember this is an alcohol you end up with. First, oxidation ends up with carboxylic acid, and reduction ends up with an alcohol. That's an important thing though, right? Now, so we can look at few other common reactions specific to aldehyde, and also I'll be talking about that in the ketone section as well, some of them. Now we can have HCN addition, hydrocyanic acid addition. So normally we have something like sodium cyanide or KCN, and this is not normally done in a laboratory setting, not in undergrad level. So this reaction, you're going to add similarly H first protonation on the oxygen, and then the CN adds up, right? So simply OH, H and CN, and sp2 becomes sp3, right? 4 single bonds. That's the goal here. But what's the beauty of this reaction? You can actually hydrolyze the CN into carboxylic acid. So you are actually adding an extra carbon, and the cyano group easily can be hydrolyzed to carboxylic. This reaction, the product is called the cyanohydrin. You see the cyano and the hydrin, the hydrate, the OH, right? Okay, so that's adding carbon. So another addition of carbon can be done with Grignard, which is RMGX, X is ClO, something like that, and you need dry ether, specific conditions. A Grignard reagent is a special one to make carbon-carbon bond. So R is actually negatively charged. It's the nucleophile. The alkyl group is the nucleophile, the yellow R here, and it will attack onto the carbonyl carbon, the electrophilic carbon, and the O will be negative. And there's 2 steps. Again, I'm neglecting the mechanism, and then we will get OH, and actually it's OMGX, but it will be removed and the OH will be in place, and then the carbon bonds to R, yellow R double prime, or just some R1, R2, something like that, right? So it's adding a carbon again to the carbonyl carbon. So 2 specific reactions, right? So the CN adds 1 carbon, and then Grignard adds whatever the carbon you need as a form of alkyl in the Grignard reagent. Okay, so the next one is a specific one. Mostly we use it in biochemistry and biological chemistry and analytical chemistry. So this one is 2,4-DNP, dinitrophenylhydrazine. So this specific reagent is special to identify aldehydes, and what we do the reaction at the reagent, and then it will make the yellow precipitate specific to aldehydes when you treated with 2,4-DNP, 2,4-dinitrophenylhydrazine, right? So this will make this compound, and this will have a yellow precipitate. And also you can do colorimetric and other studies with this one too, right? So yellow precipitate to identify aldehydes. Now, so we have one more reaction to go. Yes, these ones also qualitative identification, and there are quantitative applications too. Silver ammonia complex, and this reagent is called the Tollon reagent, and then you treat it with aldehydes with the Tollon reagents, and you're going to get carboxylic acid of the relevant carboxylic acid. It's ammonium salt actually. It's not the more important thing. More important thing is you're getting the silver mirror. So the Tollon positive means you see a silver mirror when there is aldehydes present. This is also you use it identifying the reducing sugars, because reducing sugars have a aldehydic functionality in the aldo sugars, right? So we'll talk about that separately. The other one, the silver, is actually silver reagents are expensive, so we have a good alternative, which is the Fehlings reagent. In the Fehlings reagents, you have copper sulfate, copper 2+, and basic conditions, and then you will make Cu2O, the red precipitates. That's the cheaper one, and mostly applied and replaced silver mirror tolerance test, and this is how we test urine and blood samples and so on for the reducing sugars.